Good evening, everyone, and welcome to our Friday evening astronomy talk. This is a talk. This will be a talk, our Earth Day talk by Rick Wallace, called "The Birth of the Earth." I'm Siobhan Nicholson with Pajarito Environmental Education Center, or PEEC, and I'll be the moderator for tonight's talk. Tonight's talk is being recorded. All right, so Rick Wallace has a PhD in astronomy and astrophysics from UC Santa Cruz. He worked as a staff member at Los Alamos National Lab for 30 years, working on physics simulations, and his hobbies include nature photography and astronomy education. Take it away, Rick.
Okay, thank you, Siobhan. Tonight, I'd like to, before we get into the main presentation, just do a very quick sort of news, what's been in the news recently. And this is one of them. This was from just a few weeks ago, well, about a week and a half ago. This was in Florida. And if you look in the sky, you should see momentarily something interesting show up. There we go. And you see the bright streak in the sky. That is a meteor, or what we might call a bolide, or what some people might call the crash of an alien spacecraft. But anyway, this was in Florida. And I bring up meteors because they're rather topical right now. Now, 25 million bits of debris burn up in the Earth's atmosphere every day. Most of the debris are dust and sand sized particles. Pea-sized ones can be rather dramatic. Sometimes the Earth passes through debris left from the passage of a comet or an asteroid, producing meteor showers. About 15,000 tons of material per year impact the Earth's atmosphere. Now, the Lyrid meteor shower is interesting because it peaked with the largest number of meteors per hour yesterday morning and would have been visible from Los Alamos, except that we were blanketed with a thick layer of clouds. So the meteor shower, although it peaked yesterday morning, there may be some stragglers. So if you go out tonight, the closer to midnight, the better. But late in the evening, you might see a few if you look toward the east to the south. This is debris from Comet Thatcher. And be sure and wear warm clothes and have a little bit of patience. Your eyes have to become dark adapted. Okay, on to the main part of the presentation tonight. I will be talking about the birth of the Earth. Now, I know this is Earth Week. That sounds like it fits right in, but I'm not going to be talking about things like environmental change or the evolution of dinosaurs, plants, and animals, and those kinds of things. I'm going to be talking about the formation of our solar system and the rock under our feet that we call the Earth. Now, before I go farther, I'm going to stop my video, so hopefully the slides will be a little larger on your screen. So most people realize that our solar system consists of a group of inner rocky planets, Mercury, Earth, Venus, and Mars, and then an asteroid belt of crushed rocks and dirty ice that orbits between Mars and Jupiter, and then the gas giants on the outer part of the solar system, Jupiter, Saturn, Uranus, and Neptune. And then beyond that, there are the Kuiper Belt with Pluto and some other things. Let's keep in mind that many exoplanets have now been discovered. New Kepler planet candidates are numbering something like 4,151 confirmed, and this was as of last year. There's at least one planet per star. 1 in 5 sun-like stars have planets. And if you do the arithmetic, that means that something like 40 billion Earth-like planets in our Milky Way galaxy alone. And you can see that initially we saw many larger planets, Jupiter and Neptune-sized planets. But more recently, we've begun to improve the technology, the instruments that we use to do this, and our techniques for analyzing the data. And we're beginning to see many, many more Earth-like planets. Now, supernova explosions seed interstellar clouds in the interstellar medium with processed materials. We'll talk a little more about this in a minute. By materials, I mean things like carbon, oxygen, neon, magnesium, and so on that were created within the star. And realize that our sun orbits the Milky Way about once every 250 million years. So when the dinosaurs were prominent on the Earth, we were actually in a completely different part of the Milky Way. And there are cosmic dust clouds throughout our galaxy, the Milky Way, that we pass through or that may have initiated the formation of our solar system. This is an example of a giant gas and dust cloud. This is the Pillars of Creation in the Eagle Nebula. It contains many millions of times the mass of our own solar system. It's at about 7,000 light years away. And these huge giant gas and dust clouds are compressed by the shock waves from nearby supernova. Mystic Mountain is another one of these so-called giant molecular clouds in the Eta Carina Nebula, at again about 7,500 light years away. This is the Orion Nebula. Many of you are familiar with the Orion constellation, prominent in the winter skies. This photo has filtered through IR to bring out the various gas compositions. Different colors indicate different gas. But this next one is the really interesting one for me. This is a Hubble mosaic. This was 520 images taken in 5 different colors. And the angular size of this nebula is about the size of the full moon. So this is tremendous detail. And if we zoom in to the very center of this nebula where you see the whitest parts of the nebula, you begin to see this, including this black region in the lower right. And there are some others maybe you can pick out in here as well that are very special regions. There are over 200 protoplanetary disks in the Orion Nebula alone. These are just 5 representative protoplanetary disks. The one on the right is the one that was most prominent in the last photo. The initial collapse of the gas cloud, once it started its collapse, perhaps by the shockwave from a supernova explosion, it begins to collapse, gravity takes over and pulls it together. If it's rotating, then it squashes it down into a disk. It only takes about 100,000 years for this to collapse down to the point where the material in the center of the disk becomes so hot that it ignites and becomes a star. The accretion then continues for about 10 million years until the material in the disk is blown away by the star's radiation. This is a protoplanetary disk around Elias 227. It's about 450 million light years away, and you can see some structure within this disk. Here's another artist illustration of what a protoplanetary disk might look like, and this one the star has actually begun to shine and blow material away from the center of the disk, and you have a little void area, a ring around the star where some material has begun to accumulate into a protoplanet, and that's begun to sweep the area clear of dust and gas. Here's another artist illustration. You can see a tremendous amount of dust in here as well as the gas. So as I mentioned, the gas cloud collapses. Material is pulled together by gravity in the center until the temperature and pressures are high enough for stellar ignition. Hydrogen begins to fuse into helium in the core of the star, generating tremendous heat and energy. The sun's core temperature is about 15 million degrees centigrade, 27 million Fahrenheit, and huge pressures. Very quickly, I'll mention that most of the material in the universe was originally formed as hydrogen and helium, predominantly hydrogen. Hydrogen is just a proton with an electron around it. So a hydrogen atom is, if it's hot enough and becomes ionized, that is, the electron is energized so much that it leaves the atom, then what you have left is the nucleus of hydrogen, which is actually just a proton. And so you have these protons that are smashed together at very high temperatures and densities in the center of our sun, for example, or another star. They fuse together to form deuterium. You now have in red a proton and in blue a neutron. One of the protons emits a neutrino and becomes an electron and becomes a deuterium nucleus. This fuses with another hydrogen atom, which gives off energy, and it becomes tritium, two hydrogens and one, or two protons and one neutron, which fuses with another tritium. That the same process has occurred to that nucleus, and you end up with helium, two protons, two neutrons, and a couple of excess protons thrown out to start the whole process back at the beginning again. And that generates the heat that it produces eventually the light that we see coming from a star. Now, this ignition of hydrogen fusion can be unstable. Here is a particular HOPS 383 deeply embedded protostar. This left picture is in the year 2000. The right picture is 2004. You recognize these bright stars here, and you see this little dim HOPS 383. And then in 2008, that little dim thing becomes very bright. And in 2009, it's completely gone again. So this ignition can be unstable, and these flares could heat dust and help in the formation of chondrules that will be discussed later in one of my videos. This is an illustration of planets forming in a planetary disk. This is a little bit cleaner because it's an artist concept, but you have the star in the middle, some gas and dust still around it. This area where the star is kind of blown out some of the gas and dust, and the planets have formed, sweeping out a clear area around it. Here is a Hubble photograph on the left of TW Hydri, where you have the location of the star, and it has blown away the gas and dust close to the star, creating a void. And you see this dark area here, this gap in the disk. This is an artist illustration of what you're seeing. And the idea is that we believe that a protoplanet is forming here, and it's sweeping this gas and dust out of its way and accreting that gas and dust to grow larger. This is an example of Fomalhaut B in a stellar disk. It's either a planet or a clump of material, and it has moved from 2004 to 2006. You can see in this blow up of this region where it's actually moved and it's orbiting this new SAR in an area where it's beginning to sweep material away from the disk. Here are some Hubble images. You see the white arrows, 2004. And hopefully that one's not moving either. Okay. Let's see if I click on it. There you go. There it is in 2006. There it is in 2010 and 2012. This is a photograph actually of hot young stars in Cassiopeia blowing away material. You can see this void forming around these new stars. Now, water in the solar system, water is very prominent in these giant molecular clouds. It exists all over the galaxy and the interstellar medium, in faraway galaxies, actually in quasars that are billions of light years away, have tremendous amount of water. Water is everywhere. And it's everywhere because it's very simple. It's just hydrogen and oxygen, H2O. And I mentioned hydrogen is the most abundant element in the solar system, well, or it's in the universe actually. And oxygen is one of the first elements formed after helium from the burning of the nuclear material in the centers of stars as they go through their lifetime processes. They create helium and then carbon and then oxygen and then other things like neon, magnesium, sulfur, and so on. So the water is in these giant molecular clouds. Portions of these clouds will collapse to form protostellar disks. Those protostellar disks will go through a process of aggregation of materials into protoplanets and then planets. And then the water will be incorporated into the the eventual planets in this system, as well as these objects in the outer icy regions that don't necessarily form planets. Here's a short video from NASA that talks about, in particular, asteroid Bennu, but basically the formation of the solar system.
This is the story of our Earth's formation 4.5 billion years ago, and of a little asteroid called Bennu, who's also survived until now. We have the team at NASA to thank for bringing us this video.
The Milky Way, home to billions of stars, rising and setting over billions of worlds, including our own. In this vast expanse, how did our sun, the Earth, and the planets come to be? In recent decades, our understanding of the solar system's evolution has greatly improved, but deep questions remain. To answer those questions, astronomers are preparing to visit someplace very small. Asteroid Bennu. A lump of rock and organic material, the early building blocks of the solar system, of Earth, of us. Bennu is a time capsule, and its journey takes us way, way back, 4.5 billion years. The raw ingredients of Bennu and our solar system originated in a stellar nursery, a vast cloud of hydrogen, helium, and dust. Our own sun doesn't yet exist. Nearby are hot stars like this one, quickly burning up its fuel and destroying itself in a colossal explosion called a supernova. The explosion destabilizes our cloud, causing it to collapse. In the geologic blink of an eye, 100,000 years, gravity and angular momentum flatten the cloud into a swirling disk. In the center, where molecules crash together tightest, a protostar revs up to incredible pressures and temperatures. Deep within the disk, clumps of dust not much larger than a grain of wheat are flash heated into droplets of molten rock, called chondrules. The source of this heat remains a mystery. Chondrules are destined to become the building blocks of the solar system. Coaxed by gravity and turbulence, the chondrules clump. They grow into the first asteroids, into mountains, into planets. The asteroids are rubble piles of rock, metal, ice, and organics. This large asteroid is the parent body of Bennu, a protoplanet whose size we can only guess. Closer to the protostar, a planet begins to form. And then, dawn in the solar system. The protostar undergoes fusion and ignites, revealing our sun. But the solar system is far from finished. Jupiter most likely forms near its outer edge, but just 500 million years after the sun ignites, some believe that it slowly moves inward. Its massive gravity ripples the asteroid belt, disrupting countless asteroids and comets, flinging them toward the sun. They rain down on the inner planets, hammering and remelting large portions of their crust. Did these impacts also deliver organics and water, key ingredients for life? Back in the asteroid belt, Bennu's parent body is lucky. It survives this period of heavy bombardment. The solar system cools and calms. Jupiter and its many moons assume the orbits that we see today. Billions of years of quiet follow, more or less. Then 1 billion years ago, one theory suggests a collision shatters the protoplanet. Some of the debris loosely coalesces into a new, smaller body, Bennu.
Okay, that talks about Bennu. Then it goes on to talk a little bit about the sample collection mission to Bennu. We do have a spacecraft that OSIRIS-REx that did last year successfully grab about 2 pounds of material from the surface of Bennu and is expected to return that material to Earth by about September of 2023. You may have heard of a Japanese mission that has already completed such a return. So you saw a couple of things in that video. Of course, that's most of my talk. Those of you who have other things to do can take off now if you like. But for those who want to stick around a little longer, we'll talk a little bit about the details of some things that you heard about in that video. One of which was it presented this theory of the solar system formation that is sometimes called the violent accretion theory of things clumping together and sticking together through violent collisions. There's an alternative theory to that that has come out in the last year or so, and we'll talk about that at the very end. But how do we go from these chondrules, these clumps of dust grains, into bigger and bigger things? They're too small for gravity to do it by itself. And that's the subject of the research paper I'm going to show you next, which was done just a couple of years ago. Here we go.
What we're looking at is a simulation of dust moving through gas. So astronomers actually spend a lot of time thinking about dust because dust is ubiquitous in the gas and medium between stars. And in fact, pretty much all the heavy elements in the universe are actually concentrated in little dust grains. So if you care about the things that made us or the things that made planets or pretty much anything that's not boring hydrogen and helium, you have to care about dust. We've discovered a new instability or mechanism by which dust and gas interact across a tremendous range of physical scales in different types of systems. Everything from atmospheres with rain and clouds and dust and smog, through seeds of planets, through gas and dust that fills the space between the stars and galaxies. We've been trying to understand for literally hundreds of years how planets form, and the biggest challenge has been understanding how you build the seeds of the planets. And that's one area where this could really dramatically change our picture of how that happens. It's a lot easier if I can draw it on the board and show a sort of visual example of how this works. You can start with tiny grains of dust, and these might wander into each other and collide and stick into a bigger dust grain. But then the problem is this gets bigger and bigger until you get to maybe a centimeter-sized object, and they don't stick together. Gravity doesn't pull two pebbles together very strongly, so you need some huge object in order to pull things onto it with its own gravity, and everything, in between here is just a big mystery. In the new picture, none of this in the middle actually happens, and the idea is that you just skip basically from these tiny dust grains all the way to this giant object. So you get lots and lots and lots of these little tiny dust grains, clump them all together until they become so many in such a small space that gravity just pulls them all together into this giant object. So how does this actually happen? How do the dust grains actually clump together? To explain that, let's think about stuff moving through our atmosphere where we have some intuition. Let's ask what happens if we have a giant object like a bowling ball moving through the air. You drop it out of a plane, so you push the atoms and molecules in the air out of the way as you fall down towards the ground. And if there were just the one bowling ball, that would pretty much be the end of the story. The difference is you've now got a whole fleet of bowling balls that are all falling down at the same time. So there's another one over here and another one over here, and this one's falling down and pushing the air out of the way. But so is this one. It's also pushing the air out of the way as it falls down. And so is this one, pushing the air out of the way as it falls down. And so this all streams now sort of funneled in this direction between the two bowling balls. Now this one sees this huge headwind coming up at it and gets kind of knocked out of the way by that giant headwind. So maybe this one gets knocked over here. But now that means that I'm starting to line up my bowling balls all preferentially over here, which means they're generating an even stronger headwind, knocking the gas out of their path. So this process runs away. And then potentially, if this were instead of our atmosphere with bowling balls, a swirling disk of dust around a new star, form a giant planet or asteroid seed by having all these bowling balls collapse together under their own gravity.
Okay, and as a imperfect analogy, sort of analogy to that. Think about corn that's boiling on the stove, and you notice how the bubbles are funneled between the two cobs of corn. So if you had a series of corn cobs, above these between the camera and the corn here, you might get an accretion of corn cobs. Well, let you think about that. The solar system formation cloud then might look something like this. You have the sun in the center. It's beginning to create a void where it's blowing material out. You have these rocks that are accumulating into planetesimals and eventually into planets. The outer planets are not as warm as the inner planets, so they retain some of their hydrogen, helium, and other volatile gases and become big gas balls. And you have comets that are moving toward the inner part of the solar system from the outer part of the solar system. So this accretion process is sometimes referred to as the late heavy bombardment. This is the formation of planets by high-speed accretion. Earth's water is mostly evaporated by this process in this scenario, and we thought would be replenished by meteorites. It turns out there are certain isotopic similarities between the water and meteorites, which contain a tremendous amount of water, by the way, and the water that we have now on our Earth. But the simulations of asteroid impacts on Venus from just last year suggest that these asteroids did not bring enough water to form the current atmosphere of Venus. And so there's a question, maybe these planets acquired some of their water from asteroids, and some of it was retained perhaps deep inside the planets and in the planet rocks and in the heavy atmosphere of Venus, for example. All right, here is a simulation of that process that you heard about in one of the previous videos, where they talked about the giant planets like Jupiter moving around, causing gravitational instability and throwing things out of the system that was being formed. This is a simulation with a supercomputer.
In the past few decades, our spacecraft have visited many exotic locations in the solar system, including icy comets that have orbited the sun since the planets were still taking shape. We have explored relatively tiny asteroids, ancient rubble piles held together by weak gravity. And we have found that the largest asteroids resemble the building blocks of planets themselves, all of which suggests that these objects offer clues to how the planets formed. And we have even found evidence for a violent rearrangement of the planets. Computer simulations allow us to reconstruct the formation of our solar system 4.6 billion years ago. We use the laws of physics to create these virtual experiments in order to figure out how planets took shape. After the sun ignited, most of the material around it had flattened into a disk of gas and dust. We can zoom into a simulation of a portion of the thin disk, a small piece of the universe in a box. Here, a dense swarm of objects clump together to form what astronomers call planetesimals. This simulation addresses how planetesimals form from much, much smaller particles, the size of pebbles. Pulled together by gravity, some planetesimals formed the planets, while others became asteroids and comets and dwarf planets. As the planets accreted, they carved out gaps in the disk. But the solar system remained quite cluttered. If we look at the orbits of the planets and accelerate the passage of time, so 1 million years pass by every 10 seconds, we can watch how the debris cleared. In this simulation, the giant planets, Jupiter, Saturn, Uranus, and Neptune, shift their orbit.
Shoot. Dang. All right. Well, I can't play the rest of that video. Sorry about this. We have a little technical glitch. I can't start the video in the middle. Let me just tell you the way this works out is that these giant planets will cause gravitational perturbations of these smaller objects and throw them out of the solar system all over the place. And throughout they can go throughout the galaxy, in fact. And what's left is a more stable solar system with just the planets as we know them, with a few asteroids left over to form the asteroid belt. Now, this could have happened in another stellar system in a very similar process, and may have led to Oumuamua, which is the visitor from external to our solar system that was discovered in 2017. There's at least one Harvard astronomer who thought this was not just a bizarre cigar-shaped object hurtling past the solar system, but in fact a spaceship or a space probe from intelligent aliens. Most astronomers believe that this is more likely a natural phenomena and resulted from a very similar process to the one that you just heard about in the last video. It has a rather unexpected trajectory for its time, in that it came from above the plane of the solar system out through past the sun, and then changed its course by itself. Well, why would it change its course by itself? Again, it could have been an intelligent aliens probe, but it also could have been something that was a frozen ice ball that got too close to its sun. This is a computer simulation showing how it would elongate as it passed by the sun, and this is the final result of the object. However, when we looked at the data more carefully over the last few years, it turns out that the best solution for the profile, the size of this object, looks more like this. Now, those of you who really like aliens are going to say that looks like a Millennium Falcon, so it's obviously a spacecraft. But other people would say that the recent shape is more like a cookie. They also discovered that it has a very strong detection of nitrogen, giving rise to this exoplanet Oort cloud theory. That is, this is something that formed in the outer reaches of a stellar system. In the outer reaches of our solar system, there is an Oort cloud. There's the Kuiper belt with frozen nitrogen on Pluto, for example. And then beyond that, it's even colder and farther from the sun. And there's a cloud of things that sometimes are perturbed and go toward the inner part of the solar system, and we see them as comets. And that region out there beyond Pluto is called the Oort cloud. But even Pluto has this huge area, Sputnik Planum, with blocks of floating of material floating in nitrogen ice. And so something like this could have been hit by another object, a collision that would have knocked off a chunk of such material, and then it would have, as the outer layers of this nitrogen ice evaporated, this shape could have progressively flattened like a bar of soap to lead to the object that we actually saw passing through our solar system. So it would be something that originated in the outskirts of another stellar system nearby. And there have been 4 stellar systems that were identified as possible origins for this. If it passed by too close to a giant planet like Jupiter or something even bigger, erosion by galactic cosmic rays and evaporation of this nitrogen gas, by the time it enters the solar system, it has this flattened cookie profile. And then as it exits the solar system, after passing the sun, it begins to warm up. Some of that nitrogen gas evaporates, and that causes the change in trajectory. So this is now one of the leading theories for that. Other evidence of a collision has to do with the rotation axes of various planets. Mercury and Venus are almost completely, they rotate about an axis that is pointing in the direction of the axis of the orbit of the planets around the sun. Earth is tilted 23.5 degrees. Mars is almost the same. Jupiter is straight up. Saturn is tilted 26 degrees. Neptune is tilted. Uranus is on its side. It's actually orbiting around the sun and rotating at almost 90 degrees on its side. These various tilts could be explained by collisions. There are also very fast rotations of huge planets like Jupiter and Saturn that may indicate a collision or a near miss with something in the past that sped up their rotations. Jupiter rotating so fast that it has a 10-hour day, even though you can fit, 1 million Earths into this, or some large number of Earths across this. The planet, it's so large. Saturn has an 11-hour day and 1,100 mile-per-hour winds. This is a close-up of some of the images of Jupiter's turbulent clouds. Uranus is another one. It's just so strange. Not only is it tilted almost 90 degrees to its orbit around the sun, but it has rings like Saturn. They're just not as prominent as Saturn's rings. However, they're darker than the rings around other planets. They're ice covered by carbon, so they reflect like charcoal, unlike Saturn's rings that are largely ice. Nearly twice the temperature of the planet itself, and they only contain golf ball sized chunks versus Saturn that has things from dust powder grains to boulders in it. Very strange. People have done computer simulations and found that if there were an impact between Uranus and something else that was about the size of the Earth or a little larger, it could explain Uranus's tilt, its rings, the moons that are in the same orbital plane as the rings, and its rapid rotation. You can get all of this from a single simulation of an object about the size of the Earth impacting Uranus in the past. And that was work from just a year ago. There's another asteroid, P210A2, where the dust and gravel tail from this asteroid. Now, this is not a comet, this is an asteroid, so it normally wouldn't have such a tail, but this is from a recent head-on collision. Another example of something that had a recent collision is the Neonalusta meteorite, this is actually a photograph from my meteorite collection. I have this one on my shelf behind me. It is a strong shocked iron nickel meteorite. It's very heavy, but it had an impact about 1 million years BC when it impacted the Earth. Before that, though, it has something inside it called stishovite, which is a quartz compound that only forms under a shock impact. So this was the core of a planetesimal. It was the core because it's very heavy elements, iron and nickel, for example. So it's the core of a planetesimal that was destroyed by a collision that occurred millions of years before it impacted the Earth. And let's look at the moon. There are several theories for the formation of the moon. The capture theory, a giant asteroid formed somewhere else, was captured by the Earth's gravity. This is the predominant, the main theory for the moons of Mars, for example. Accretion theory, the moon formed along with the Earth. Or the fission theory, the Earth spun so fast that at some point during its history that some material broke away and began orbiting the Earth. And finally, the giant impact theory. The young Earth was obliquely collided with some Mars-sized object, which has been called Theia. The debris coalesced then into the Earth and the moon. Now, the Apollo samples of moon material show that the Earth and moon material is very similar. So it was not formed apart and captured unlike the moons of Mars, for example. That's not likely. The Apollo samples, however, showed that the Earth and Moon material is not identical. It's extremely similar, but not identical. So it's unlikely that there was some fission of the Earth that produced the Moon, or co-accretion of the two together, because they would even be more similar if that had occurred. So those theories are not looking too good. There are pale gray anthracites, molten rock cooled, and then lighter material floated to the top, and also dark regions, basalt from molten interior. But the moon has no volcanoes on it. So this molten material came from some other process other than volcanoes. The moon is unique in the solar system. All the other planets have much smaller moons relative to the size of their planets. Our moon is just huge compared to the size of the Earth. And so that suggests that it formed in a unique way compared to the other planets. Now, this last year was there was a paper produced that really looked into a very detailed chemical composition, and in particular the oxygen isotopic composition of the Earth and the Moon. So again, the theory of this planet Theia, about half the size of the Earth or about the size of Mars, smashed into the Earth about 4.5 billion years ago. The collision produced enough heat to create magma oceans and ejected a lot of debris into orbit around the Earth, which subsequently coalesced into the Moon. The Moon and the Earth are nearly identical in composition. Again, the Moon has fewer heavy elements, iron, for example, and less hydrogen to produce water. The larger Earth retained the heavier elements, and the heat boiled lighter ones off the Moon, so that the rest of the elements just mixed together. The oxygen 16 to 18 ratio on the Moon is larger than the Earth. That is, the lighter isotope of oxygen is more predominant relative to the heavier isotope on the Earth, on the Moon, rather than the Earth, especially in the Moon's mantle, which is the deeper rock, where you would expect to see more of this material from Theia. So the conclusion was that the Theia formed near the Earth, but slightly further away from the sun, thus retaining more of this lighter oxygen 16 isotope. And that a chunk of Theia may in fact remain buried inside the Moon to give rise to these, the fact that this deep molten material that has come up to the surface of the Moon has this oxygen ratio characteristic of this object Theia. So here's a video that sort of summarizes all that in terms of the giant impact theory for moon formation. Simulations of this type of formation of the moon, this giant impact theory suggests that, in fact, the moon may have been much closer to the Earth, maybe just thousands of miles away, a few thousand miles away, as opposed to the 250,000 miles that it currently resides at. And then as the Earth was rotating very fast after this collision, the Earth's rotation slowed down, momentum was transferred to the moon, and it gradually moved away to its 240,000 mile position today. Now, this is a paper that just came out in the last few weeks, Geophysical Research Letters 2021, and they have been able to map some blobs that they believe are remnants of Theia buried inside the Earth. There are two blobs, each one is millions of times larger than Mount Everest, and they first noticed this because there was lava from certain Samoan and Icelandic volcanoes that was chemically different, and the radio dating was also quite different. So slightly different ages from volcanoes around the world in these specific volcanoes. This is an animation showing where they believe the remnants of Theia are buried about 1,800 miles below the surface of the Earth. And these blobs are 1.5 to 3.5 times denser than the rest of the Earth's mantle, and also a little bit hotter. So low shear velocity provinces, these materials, could interfere with the mantle convection and reduce the magnetic field above them, which could also potentially explain something called the South Atlantic anomaly, where we have a lower magnetic field over parts of South America and going into the South Atlantic. And this poses a problem for satellites. They're less protected from solar and cosmic radiation when they pass through that area. And so they have to shut down a lot of their electronics as they go through that area. Even the space station has some issues when it flies over that area. And these were partially mapped using seismic waves from earthquakes and things. So if the Earth were reshaped by this huge impact, what would happen if Theia had missed? That is, what if there were no moon? Well, the large moon stabilizes the Earth's rotation around an axis that's tilted at this between 22 and 24.5 degrees. The Earth would wobble or precess far more than that small range if it did not have a large moon stabilizing the rotation. Unstable precessions or tilts would lead to unstable climate change. Remember, the tilt of the Earth's axis is what gives us winter and summer as the Earth orbits the sun, and the tilt is either toward the sun or away from the sun. So an unstable amount of tilt would lead to unstable climate change, perhaps rapid and more extreme ice ages and hot periods, and perhaps quicker changes. No tides would be there to form tide pools, which is one of the locations proposed for the formation of early life. And would this, in fact, prevent life from taking hold at all? So this could have a dramatic effect on the Earth, and also a dramatic effect on the probability that other planets around other solar or stellar systems might have life. Because if this were a very unique event, then perhaps that wouldn't have happened to other places in our galaxy. However, there are arguments on the other side of this. Some other planets do have stable rotation axes without a large moon, so maybe it wouldn't be quite as unstable as we thought. Also, if it's a relatively small precession in the axis tilt, a slow precession might be acceptable for life. And life may have arisen near undersea vents. And we see these black smokers at the bottom of the Atlantic that thriving with all sorts of life. And in fact, one of the theories for the potential life on some of Jupiter and Saturn's moons, like Enceladus, are that beneath the frozen surface, we know that there is a liquid ocean. And that liquid ocean at the bottom of it may have geothermal vents, just like these. And so life could arise there. So it's not at all clear that these consequences on the top part of the slide would hold true. but it's an interesting concept to think about. This is an example, again, I've showed you the slide before, but Earth is not the only planet tilted at 23.5 degrees. I mean, look at Mars, Jupiter, Saturn, Neptune, and so on. They all have stable tilts, even though they don't have these huge moons relative to the size of the planet. And I mentioned this, that the moon could have started out much closer to the Earth, and then tidal interactions would have caused the moon to drift farther away as the Earth's rotation slowed. And it's still drifting away at about an inch a year. Okay, now beyond Uranus and Neptune is something called the Kuiper Belt, and this is where we find Pluto. They're pristine frozen objects left over from the formation of the solar system that are out there, and in particular, our New Horizons spacecraft took this high-resolution image. It's been processed for over a year now, and they finally processed it to the point where this is what they think it looks like. A potato, but it's not really a potato. This is Arakoth in the Kuiper Belt, and it's has very uniform coloring and composition and a very gentle attachment. The rotation of this object is looks like two flattened lobes in very close alignment of their poles, indicating a more orderly merger from the collapsed cloud. And if that's the case, then these lobes were once separate bodies. They formed close together at relatively low velocities, orbit each other, and then eventually grew closer and closer together and gently merged. So this is formed by gravity-driven collapse of a cloud of solid particles in a primordial solar nebula, not by this violent planetesimal formation of high-speed hierarchical accretion through collisions. The uniform color and composition suggest nearby materials, and this more orderly merger is suggested by the flattened lobes and close alignment of the poles. Another merger that we suspect is within the planet Mars. Mars may be composed of two planetesimals. Meteorites from the magma portions of Mars show distinct types of, in this case, deuterium to hydrogen ratios. Remember, deuterium is a hydrogen atom with a neutron and a proton, whereas what I'm calling hydrogen here is just the proton. Meteorites from the crust of Mars, so these are meteorites where some object has hit Mars, knocked material off of it, and meteors strike on Mars. That material, some of which floats through space and ends up on the Earth. We can tell it's from Mars through various chemical compositions and other things, but it's very clearly from Mars, and there are two very specific types of material that we see in these so-called Martian meteorites. Here are two examples, one from the crust of Mars and one from the deep magma lava of Mars. So the traditional theory was that worlds like Earth and Mars began life as liquid globs of smoothly blended rock, but these Barnes and her colleagues from exactly a year ago suggest that beneath Mars's rocky shell, there are two types of Martian material, unmixed relics of the baby planets, planetesimals, that came together to form Mars. This is based on the deuterium to hydrogen ratios of water, and Mars's atmosphere itself has a very high deuterium to hydrogen ratio because the lighter hydrogen is more likely to escape over the 4.5 billion year history of the planet. But the meteorites on Earth have these two very distinct deuterium to hydrogen ratios that were unchanged, unlike the atmosphere of Mars, over the history of Mars. This suggests that there are these two distinct components within Mars. So the questions become, do planets form by accretion through high energy collision? Or do planets form by gentle accretion of pebbles directly from the original gas and dust cloud? There is evidence of both processes occurring in our solar system. So we need more data and simulations to determine the dominant mechanism. Of course, both mechanisms could have occurred at the same time. The inner planets may have been formed by these planetesimal collisions, and the outer regions of the solar system beyond Uranus and Neptune, the Kuiper Belt, and perhaps where the comets are out in the Oort cloud, may have been formed by a more smooth, less violent process. But that still remains to be determined. So that is my take on the origin of the Earth and the origin of the solar system. In fact, next week you will hear from Dan Reisenfeld about what will happen about 5 billion years from now when the sun begins to run out of its nuclear fuel that it's burning, and that will lead to the end of the solar system. And Dan will tell you all about that next week. So thank you for being with me, and if there are any questions, I'd be happy to try to address those now.
Hey, thank you, Rick. That was interesting. I really appreciate you keeping up with the latest results and hypotheses and passing them on to us. It's a good way for us to keep up with the news a little bit with you doing the work. It's great.
Keeps me awake too. It gives me something to do.
Okay, good. We do have some questions that came in. Let's see. Okay, here's one from Marilyn who says, how are the ages of meteorites determined?
They're largely determined by nuclear cosmochronology. What that means is that there are isotopes of materials. So, for example, lead or other materials, uranium is sometimes used. There are actually about 6 or 8 different nuclear isotopes that are very long-lived. And we can look at the ratios of those isotopes that are related to their parent nuclides, that they're heavy elements, heavy isotopes that decay into, they're radioactive, and they decay into more stable isotopes. So we look at the ratios of the stable isotopes, and that tells us something about the parent isotopes and what their relative composition was when they were originally formed before this nuclear decay began. And these isotopes decay at very steady rates, and we can determine those rates in a laboratory. And so we know very precisely how long it takes from one of the parents to turn into one of these so-called daughter isotopes. And if you look at these ratios of daughter isotopes, we then get the ratios of the original parent isotopes. We know how long this decay was going, the rate of this decay, and we can then tell how long that decay occurred, and that dates the parent, the formation of the parent isotopes. So that's a very long, history behind it, and it's a very complex field of study. I think Galen actually gave a talk one time. He gave an entire talk on just this topic. And if you're interested in more information about that, you might put that into the comments somewhere, and Galen might be coerced into giving his talk again. But we rely on those for dating anything astronomical, like asteroids, for example. The age of the Earth is a little more difficult because the oldest objects we have from the Earth seem to be not quite as old as the Earth itself, almost, but they may date from that huge collision between the Earth and the Moon. And the Earth's crust is continuously moving, and parts of the crust are being subducted underneath other parts of the crust as the continents drift. And because of that, much of the crust is renewed, and so it doesn't work as well for the Earth. But it works extremely precisely for asteroids.
Okay, great, thank you. We have, let's see, quite a few questions about collisions. Oh, Galen points out that there is a video of his talk, The Age of the Earth, on our PEEC YouTube channel, and I'll try to get a link to that channel to send out. And a recording of this talk will be available on our YouTube channel as well. That should be in about a week. It usually takes us about a week to get all the videos edited and posted onto the channel. So there's, I just put in the chat a link to PEEC's video YouTube channel. So if you want to take a look. We also have on our website, peeknature.org/learn/videos, you can see a whole list of all the videos that we have available. Okay, let's see. We have a bunch of questions about collisions. So we're going to move on to collisions. So Gary asks about the spinning of Uranus. And he's wondering if it might have been caused by a hit the planet took as an object in motion stays in motion, he says, or is the outer shell of Uranus heavier on one side and that causes it to spin from north?
Yes, it certainly would. And then you would have to ask the question, why is one side of Uranus heavier? And in fact, that does affect the axis of rotation. We just found out, in fact, I just read this, Carolyn found it about a couple hours ago, that there is a new paper suggesting that the Earth's rotation, its axis has tilted slightly because of the melting of the ice caps due to global warming. And the melting of the ice caps has shifted the material around on the Earth. And so that has actually shifted the tilt of the Earth's axis just very slightly. So that certainly could happen if you had a much bigger effect. How would you have that? Well, if it's collapsing from this dust cloud, you would expect gravity also works on all pieces of it uniformly. That's why all the planets are spheres, all the large moons are spheres, because that's the way gravity works. It pulls everything toward it equally from all directions. And so you would expect it to be uniform, unless there was something very strange that happened. One thing strange that could happen would have been a collision. So there are two reasons to suspect there may have been a collision. One is a collision would have changed the tilt of the planet. It would also be able to explain the strange tilt of the rings around the planet and all the moons that are orbiting in the same plane, plane as the rings. So all of those things are consistent with a collision. If it had been a collision and part of this object that collided with it stayed on one side of the planet, like these asymmetric blobs on the Earth, inside the Earth, for example, that could have caused a shift in the rotation as well. So yes, that could be an explanation. The question then is what caused that difference in the density of the planet, and that could have been a collision. So all things seem to point toward a collision on Uranus.
Okay, awesome, thank you. And then you mentioned that Jupiter and Saturn have like sort of suspiciously fast rotation rates. Is there a particular rate of rotation that we would expect from theory in the absence of a collision, let's say?
Yeah, you can get that there are simulations that look at a gas cloud collapsing. We don't have all the details of the coalescence of the dust grains and so on. But in general, those things are going to be orbiting with the orbital rotation of the dust cloud. And then they're going to be rotating within that orbit at a speed that will be governed by that original dust cloud angular momentum or rotation, modified by if there's this early bombardment phase where chunks of things are colliding with each other and causing collisions, then those are also going to change the rotation rates. And what we've observed in various planets is that we don't see huge objects like we would not expect those objects, given the simulations, to have such fast rotation rates just from the collapse of this gas cloud. They could be fast, but probably not that fast. And so a collision, for example, Mars has these two things stuck together perhaps inside of it. That may have been an extreme collision, but maybe not, because they're still retained their composite component shapes. And so that may have been a less extreme collision, and it's rotating about the same as the Earth once every 24 hours. So you might expect those things to rotate in, I don't know, 30, 40, 50 hours, something like that for these huge planets, maybe hundreds of hours. Mercury rotates in days, but that has to do with tidal interactions with the sun. But the rotation rate of the Earth after the collision, according to these simulations, after a collision with Theia, was expected to be about 1 day, would have lasted about 2.5 hours. So it's moved angular momentum from the Earth, that rotation, slowed the Earth's rotation and transferred that momentum to the Moon, and hence the Moon's orbit has become larger and larger, farther away from the Earth. At the same time, the Earth has slowed down to its 24-hour period now. And so a collision can speed things up very fast. Whether that's what happened in Saturn and Jupiter, I don't know, because we don't have enough of the physics really precisely laid out to completely trust the numerical simulations. But what we do have suggests that their rotation rates should not be that fast if there were not some sort of collision.
Okay, great. And then talking about Theia, Chris is wondering if there is any relationship between deep mantle plumes that create hot spots on the Earth's surface, like Hawaii, and the blobs that may or may not be parts of Theia.
Right. Yeah. The the blobs are slightly hotter than that portion of the mantle, the rest of the mantle, and so that would come to mind. But experimentally, we see these plumes occurring in the middle of the Pacific, the Hawaiian Islands, for example, and other places where you do not have the blobs directly underneath them. There are 2 blobs. They're kind of spread out, but basically the biggest one is under South America and toward the Atlantic side of South America. There's another one that's on another part of the Earth, not quite in the exact opposite end, but moves around a little bit. But there really aren't these blobs, as far as we can tell from seismic mapping, that occur in the locations where these plumes occur. And so they seem to occur in areas that would be, the origin of which would be higher in the Earth's mantle than these deep blobs are. So we don't think that's what caused the plumes. That doesn't necessarily give you an explanation for the plumes. And you'd have to talk to a seismologist or a volcanologist to find out what the current theories are on that.
Okay. All right. So we have then just a couple more questions about some of your images. And let's see. Ooh, where did they go? Okay. Francis is wondering about the direct image of the extrasolar planet.
Okay.
How far is it from its central star, and what angular resolution is required, and what wavelengths are required to take a picture?
Yes. Well, first of all, it's done with infrared wavelengths, and the infrared, it does not give you the precision that you would like in the angular separation, but it does cut through a lot of the dust. And so you need the infrared in order to be able to visualize that dust. Let me see if I can quickly get to that photograph. So we have a couple of these. And yeah, I'm still sharing. So this is the distance from the Earth is only 25 light years. So that means that the angular distance here is, I don't know exactly what it is. You might be able to figure that out. But it's small enough that it's within the angular resolution of the Hubble Space Telescope. Now you see that the resolution is not great on this. You see blobs. And in fact, the original, I don't know if you can see my arrow, but this little tiny box shows the original blob. So it's barely resolved by the pixels in the image, but it's definitely a brighter spot. And that is 25 light years away. So we can only do these with the nearest objects. I don't have a distance for here, but you might expect these to be roughly maybe the distance of Jupiter or Saturn, something like that. Certainly not the Earth. That would be too close to the star. So that's not a precise answer, but a rough idea.
Okay, cool, thank you. And then there's one final question about, let's see. Oh yes, about if the Tucson, Arizona photo of the Oumuamua origin, if that was taken from PEEC telescope.
Let me go back to that. The answer is no, but let me try to be more precise. This is an artist illustration. It's not a photograph. And in fact, it says in the lower right corner here, illustration. When they looked at the data that they had, this is a numerical simulation. This is the simulation result, as it says here. This one looks like a photograph. It's really well done, but it is not. It is an artist illustration, and the illustration is based on the reflectance data that was received from a large number of telescopes scattered throughout the Earth. Actually, the largest telescopes we could get that had reflectance, that they could get, that had reflectance data. And they kind of mapped the reflectance of this object to try to get an idea of, as it's rotating, the reflectance changes, and the speed of that change in reflectance has something to do with the dimensions of the object that's being rotated. And that's how they calculate the shape of the object. And so in the previous one, they knew that it was not very wide, not very thick in the thickness dimension, but they did not have very much data on the dimension looking into the screen on this picture, and that dimension looks more like this. So that previous artist concept that we had was sort of looking at this edge on, where you're only seeing the length of the thing. But this is just based on the reflectance data, and it is an artist's concept of what that data suggests, not an actual image.
Okay, great. All right, Rick. Well, I want to thank you very much for your time this evening. This was a fascinating talk. I learned a lot of new stuff, so that's exciting. And I want to remind you all that next week, as Rick mentioned, Dan Reisenfeld will be here to give sort of a follow-up, if you will, maybe, or a prequel to this talk about the life and death of the sun. So that will be fascinating as well. So please do join us for that one. All of these information about these talks and other information is available on our website, peaknature.org. We've enjoyed having you guys here. And again, thank you very much, Rick. And I hope you guys all have a wonderful weekend.